Welcome back, everyone, to our next episode of DC Thursday. I'm Pete Soderling. I am your guide through the wild west of the data ecosystem, and we're happy that you joined us for another episode. Today, we're going to be talking about a really interesting advanced topic in machine learning. Actually, two topics. One is adversarial machine learning, which we'll learn about more briefly. And the other is federated learning, which is an interesting technique recent that helps us separate the models from the data and satisfy some privacy requirements. So fortunately, we have a great expert in the field to join us and to illuminate these topics for us, Nathalie Baracaldo. Nathalie works at IBM. And Nathalie, we're really excited to have you today. Thanks for joining us.
Thank you. I'm very excited to be here with you today.
That's great. So just to make sure that I get your title right, Nathalie, you're the manager of AI security and privacy solutions, and you're a research staff member at IBM. Is that right?
That's right. Yeah, double hats, two hats.
Great, two hats. Two hats. Well, I want to start with some of your education and the earlier part of your career, which is something we typically do here to better understand the context with which your interest in data comes from. So talk to us a little bit about your PhD. Your thesis was on insider attack detection. Can you tell us more about that and what that means?
Yeah, so I think it's a really exciting topic because organizations usually spend a lot of money creating IP, intellectual property, and a lot of different assets. And the problem with insider is that basically the employees that you're trusting all of the sudden could rush and start trying to get or steal some information, extract some information, or sell some of your intellectual property under the hood. Sometimes they are also interested in just sabotaging a company and so forth. So it's a very big problem. Actually, there's a lot of big profile cases. I'm sure you know which ones I'm talking about. And it's very difficult to actually detect before these incidents occur what's going to happen. So my thesis was all about detecting before they occur, who in a company seems to be likely to commit one such insider crime. And the idea was basically try to combine the risk assessment of profiling different employees, depending on the accesses, depending on how they behave, what types of emails they are exchanging, a whole plethora of information, and put it into a machine learning model, combine it with risk and trust, and based on the behavior, and basically decide when we should be monitoring somebody closely. So that was the overall idea of the thesis. So it's a really exciting topic to work on.
So it's basically a sort of age-old security concern, which is insider threats. But then you applied a machine learning or a data lens over the top of it in order to try to gain better insights or make more efficient decisions.
Exactly. And then one other piece that was really important was incorporate that into the access control system. Because what happens is that if you don't have that connected to the access control system, then if it's somebody manually verifying and removing the different accesses without knowing what's going on, it will take forever. And frankly, it's not going to be very efficient. So the next piece that was incorporated was adding it to the access control system. And sometimes you don't really need to remove accesses to everything, but rather have the assets in the company and the information in the company rank by like very relevant. So that's highly risk and less relevant. So we would remove access to the things that are very relevant and very important, and you really need to protect these assets or intellectual property. So we stop that with the access control. The idea being that we are really perceptive of what is going on and preventing those data exfiltration problems.
Okay, that's interesting. So did this system work its way into industry anywhere?
I don't think so. I don't think so. There are a bunch of different issues. Some of the aspects where, for instance, we were proposing monitoring certain actions in social networks and so forth, which actually are privacy sensitive. And also collecting all that information, it's kind of difficult in some cases. It may be good for military settings, for instance, because there people do not have any expectation of privacy necessarily. But for certain companies, especially in Europe, there's a lot of legislation. There are some approaches that exist out there, and IBM has some. But I don't think it's as kind of big as a thesis, which was really an exercise of understanding different factors and combining them. Yeah.
Okay, understood. So then how did you end up going from your studies and your PhD to IBM? Like what's the story of that journey?
Yeah, that's actually they offered to have me as an intern. I went for internships first, and I kind of liked it there because people are very, very knowledgeable and the teams are super exciting. And when I graduated, they offer a research staff member position. So I guess they also like me. And I came back as a research staff member. And I started just working in projects that were very different to what I did during my internships. And yeah, so it's one of those things that IBM research is so big and varied that there are a lot of different problems you can work on.
Okay, got it. Well, let's talk a little bit about adversarial ML, because was adversarial ML related to your thesis or not?
That's a really interesting question. So you heard me talk about we have a bunch of data and then we want to create machine learning models. One of the issues that we have in insider threat problem is that the data that we're collecting is actually coming from employees. And we are trying to detect suspicious or malicious employees, but guess who's providing that data? The employees.
The employees themselves.
Right. So there was a lot of potential to actually for them to poison the model and start creating kind of backdoors or reductions in performance of that machine learning model, so that at the end of the day, you get a very bad system and it doesn't matter how much you invest on it, right? So I tried to add a chapter on that in my thesis, and my advisor said it was not a good idea. But this kind of kept in the back of my mind. And after that, when I started working in IBM with IoT devices and trying to create machine learning models on top of those devices.
Okay.
So there again, you have, and I guess my mind, it always wonders that way. And it's really a threat that you have all these devices and you're making important decisions. And do you actually have a way to monitor that somebody is not manipulating those devices and providing you data that it's not what it should? So there I started expanding more and really starting to create solutions to solve this type of problem. And I realized I didn't mention what a poisoning attack is or anything. Yeah. But here, basically what I mean is the machine learning model, it's like a black box that you usually train with a lot of training data. That's kind of one of those things that you need to get a lot of data, especially if it's a neural network or something like that. And then this data is assumed to be usually when you're talking about like standard machine learning, you're just usually talking about data that it's clean, that it ideally kind of covers the distribution of the entire population. So if we are talking about insider attacks that you brought up before, then we would be assuming that the data covers very well the things that people are necessarily doing and things that they didn't. And A poisoning attack basically is when somebody manipulates the data so that the decisions that the machine learning model provides are really either bad, so that the system performance it's downgraded, in which case at the end of the day nobody's going to use the model, and people are just going to be like, oh, this is always giving me the like worst predictions possible.
Mm-hmm.
Or there are other types of attacks where, for instance, an adversary is really interested in misclassifying a sample, and they add certain triggers as part of the sample. So just a super intuitive and I think a scary case would be you are driving in an autonomous vehicle and there's a stop sign. You are kind of relying on your vehicle to be able to detect that stop sign if it's a fully autonomous vehicle.
Mm-hmm.
But you don't want to crash into another car. You don't want to get a pedestrian or a pet or any other kind of bad situation. And what has been shown is that if the adversary has access to some of the training data, that that stop sign is going to be misclassified.
Mm.
And if your car doesn't identify that there's this stop sign and it thinks it's a Jill, there's a bad situation. And that's just one of those examples of how things can go south. And you can extend it to different critical applications like airports or anything where you really need to a life-death decision that's actually very dangerous. So
Got it. So you became very interested in these abuse cases of training data where attackers could potentially poison the training data and cause the system to classify something incorrectly.
that's right. Yes. And I think there are other types of adversarial machine learning attacks, but I really think this one is in particular important to solve, because if from the beginning you cannot have a model that you trust, then it doesn't matter any of the other attacks. So the other attacks happen at a prediction time, and they don't manipulate the training data. But if from the beginning you're broken, well, I guess in my opinion was like, we first need to solve the issue that we gotta train the model. And
Right.
that's why I'm very excited about providing solutions to solve that problem, that poisoning problem.
Got it. And so what are some of those solutions? I'm curious to understand how you protect a model from something like this.
That's a great question. There are different scenarios. One of the works I have, and the first one actually that I did in this area, was related to considering the contextual information of where the data is coming from to identify whether, for instance, a potential source is providing wrong data. So imagine an IoT scenario where you have a lot of devices, IoT devices, deployed to an edge. And one of the use cases is, for instance, if you have a city in a country that is very polluted, and the mayor of that city is trying to create a machine learning system that allows them to detect when certain factories in that city need to be shut down so that the air quality for everybody is good. So I think if I live in that city, I am all for it. I like the thing. But at the same time, there are profits. So there's an incentive to manipulate that data. And the devices that are distributed to basically monitor the air quality can be manipulated easily, say to very close to a factory, so that the system would not detect when that factory is causing a bad output. And the idea there is that you basically, as an adversary, they don't have really access most of the time in an IoT system to manipulate all the different factories or all the different sensors across the city. That's probably not realistic. But they have access to certain of those and they can manipulate the data that's
Mm-hmm.
collected there. So the idea is basically to understand how that contextual information can be incorporated as part of the training process to drop data that it's really reducing the performance of the model. And there were, before I started working on this, there were other approaches, but because they did not use this contextual information, they were super slow to train. And you also want something fast. Otherwise,
and what's an example of contextual data?
The firmware of the device, of the IoT device, would be, for instance, one of those contextual data. If you know, for instance, that there's a bug or a exploit in a device, and you know all this information about the devices, you can probably verify certain versions of all the IoT devices as contextual information. That's one example. Another one could be geolocation. So different geolocations around the city would you can filter and organize your data that way, then start verifying how the data.
So the idea here is that you would reject data that came from an unknown device identifier, or if a device had been moved from the geo that you expected, you would reject the data that that device was sending. Is that the general idea?
Not exactly. So what we would do is basically take all the training data. Let me just explain first how it usually happens. So you collect all the data and you train a single machine learning model. That's the vanilla case, unprotected. But here we have this protected data, this data that came from different sources, and also next to it, we know where it came. We know all this contextual information. We know the firmware and so forth. So we basically take the training data and sort it based on a particular feature of that provenance information, that contextual information, and start training models and verifying for a group of devices, for instance, that had that type of firmware, how they are affecting your final model. In some cases, if they are really dropping or reducing the accuracy of your model, you don't want that data because then you know that it may be coming from an infected device or it's being exploited.
I see.
So it kind of gives you a way to take all the data, contextualize it, and see how that group of data, as opposed to a single sample, affects the entire model.
Got it. Okay, interesting. And so then some of this work manifested itself in an open source project at IBM, is my understanding. Tell us about that.
Yeah, so this is a very, very big library. It's called the Adversarial Robustness Toolbox, ART for short. And this, it's huge in that it basically tackles different types of machine learning threats across the pipeline. So today we have been talking, because I work a lot in poisoning, about the first stage, which is poisoning data. But then there are other threats related also to evasion. So you already have a model deployed and people try to manipulate that the data that comes for prediction to get it misclassified. We have also attacks and defenses for those. We are also have things related to data exfiltration from models. So imagine that, Pete, you are part of a training data set and somebody really wants to know if the model that they are seeing has your data. So they would start trying to see if that's the case. So we have attacks, defenses, we have metrics, because what I like to say, it's what you can't measure, you can control. So we also have metrics in there for all these types of attacks and defenses.
I see. And so it sounds like quite a large project. How many people across IBM worked on this project? And in other companies, were other companies involved as well?
So originally it was an IBM project. So I started there from the beginning and it grew. Right now, I think we are at least 15 people working on that
Mm-hmm.
one way or another. But it's actually open source now.
Mm-hmm.
So, and it's open to the entire community. People are participating. I actually don't remember the number of stars that we have, but it's a huge, huge effort.
Mm-hmm.
People are contributing to it, and this is a very active field. So there's a lot of energy going on in there. I definitely invite you all to check it out.
Great. Yeah, I hope our users check out the adversarial robustness toolkit. It sounds interesting and like it solves some sophisticated problems.
Yeah. It's still a lot of. It's not an easy problem, so I think it's great that we have that one place where the community can add their attacks, because the attacks change a lot, and also their defenses. And this is kind of one of those exciting fields where I don't think things are fully solved.
Mm-hmm.
So
Mm-hmm.
if
Mm-hmm.
you have an idea and you're curious about it, I think it's a good research topic.
So then I guess that makes a little more sense to me as to how you got into federated learning, because ultimately in your career up until this point, you were dealing with data from multiple sources, sometimes being aggregated into probably a single model. What are the parallels between what you were working on at this time in the adversarial ML, and then sort of how you got interested in federated learning? Walk us through how that transition happened.
That's a good question. So sometimes one issue that we have, and this had happened since my thesis actually, is that getting quality training data is not easy. Uh, People have private data that they don't want to share. Enterprises are subject to legislation, so they sometimes cannot move data from one place to the other and move it to a centralized single place. There's like GDPR, the HIPAA here in the US. Really, you cannot transmit all the data to a single place. And at the same time, I personally feel very strong about privacy. And the fact that we are building these models, and I think ideally we should not be collecting that many data points about everything that we do.
Mm,
So from that perspective, it's actually a good segue to go to federated learning, where you can
mm,
tap to a lot of data that you didn't have access before. So if Pete, I want your data, you don't have to give it to me, or we don't have to transmit it to a central server, but we can both collaboratively find a single model for both of us.
mm,
And you don't need to see my data either. So from that perspective, I think it's one of those breakthroughs that can help the society and the companies and everybody to get better models.
mm-hmm. Yeah, of course. Um, I guess the classic example of federated learning is the autocomplete that we see in many mobile keyboards now, right? Do you want to walk us through that and how that's an example of federated learning? Then we'll talk a little bit more technically about how federated learning works.
Awesome. Yeah, so I think everybody in the audience actually has a mobile device, I would think.
Mm-hmm.
Now, when you're typing, you probably are doing like this, and you notice that you get this prediction for the next word.
Mm-hmm.
Now, have you ever started wondering how they are predicting what's the next word? That's when the machine learning model comes in. So there's a machine learning model that helps them predict, based on what you have typed so far, what's going to be the next word. Now, to train that machine learning model, you basically would need all the data from everybody, what people are typing, which clearly Apple or Google, they don't want to get that data. that's a lot of private data. There's a lot of liability. Like, no, there's no way. So federated learning comes into play in that each of the phones that you have, that people have in their homes or with them, they basically contribute to the training of a single model that helps everybody predict what it's the next best word, without getting any of the training data, which in this case is the text messages that you're writing. So those stay in your device. Those are yours, and they are kept in your device. No transmitting, but still we get like this really good predicting model that benefits everybody.
Got it. So everybody has come across federated learning at some point, literally through their mobile keyboard and the autocomplete and the predictive text.
Yeah, so you're already using federated learning even if you don't know.
Right.
Yeah.
Well, I also know that some of the history of federated learning was literally sort of about mobile devices, right? Because that's such a great example of devices or sensors on the edge, if you will. And so it seems like some of the earliest federated learning interest was based on these mobile type use cases. Is that fair? And can you take us through a brief history of the origin of federated learning?
Definitely. So the first paper that used the term federated learning came in 2016, and it was by Google. And they were describing this use case about people, they trying to create one single machine learning model for this smart device that problem we were just describing. So I guess the first set of works were really either from Google or Apple trying to do this to protect the privacy of their smartphone users. Yeah, so that's the inception. Here, important is that there are some assumptions that are made that simplify the problem. For instance, we all have the same device or the same software, so probably things are already annotated. We don't need to go into a lot of pre-processing that's different for each device. So from that perspective, that step, it was assumed initially to be kind of done and simple. But as we started seeing this and trying to apply it to the enterprise setting, we realized that there are a lot of different aspects that need to also be considered. So enterprise settings, for instance, we have Watson Health trying to use federated learning to predict based on images like x-rays and so forth. There, each hospital may have, or each site may have a slightly different data, and it may be annotated differently. We need to do a lot of pre-processing and so forth. So that's one of the differences of what we are seeing, and what I'm working on is really try to take the federated learning and make it available for the enterprise setting. Another like super huge difference in what we are seeing in the trend is that, think about smartphones again. How many of people do we have? Lots of people.
Billions.
Lots of devices. So training there, the algorithms, you don't really need to worry about including everybody necessarily. And it's simpler in the sense that you have so many people contributing. But in an enterprise setting, imagine like 5 banks. You cannot do subsample. You really need to make sure that you're kind of considering how the banks are doing, make sure that you have your model affected the right way by each of the banks and so forth. So the scale is also dramatically different. The data is different. There's no pre-processing. So these types of problems, I think, are slightly different from what the original federated learning was designed for.
I see. So that this is the modern era of trying to take federated learning into the enterprise. Well, that makes a lot of sense. Well, why don't we talk a little bit about how federated learning works at a little bit deeper technical level?
Sure.
Do you want to walk us through that?
Yeah, I can show a slide if that's
Oh, that
okay.
would be great. Let's do that.
All right, let me see. So yeah, so I wanted to show this slide because it kind of really demonstrates what we are doing and the different entities on the system. So, okay, here we go. So this is how this works. The magic happens here. So imagine these parties, and just because we have been talking about smartphones, each of these parties is actually a smartphone. You can think about it. And each of them has their own training data. That's why I put this little thing in each of them. This training data can have something like X, Y. So this is the sample, for instance, an image or your text message, and the label, if we are doing something like a classifier. And so the aggregator here, this one, it's going to orchestrate the entire training process. The aggregator basically first sends a query to each of the participants. This query, you can understand it as something like, give me the gradients for this neural network after you have trained. So each of the parties in that case will take that query, will use their data to train or to answer that query, and then send back the reply to the aggregator. With that, the aggregator takes all those replies, which again, they don't contain any private data. They only contain the information about either weights or gradients. If we are trying to train something based on neural networks or SPN, something like that. Or if you can also even train decision trees, in which case this reply is just the counts. So it's not really the training data itself. The aggregator takes all of those and creates a single model. So that's basically the entire magic about what happens underneath the hood. The important thing here is that we never move the data. So your text messages are yours if that's what we were using for training. So that's the idea.
And what algorithm does the model use to aggregate and create the combined model?
There's a plethora of algorithms, a lot of different algorithms. Depends also in several things, the type of machine learning model that you're training. So sometimes you are training a neural network. It's very easy to aggregate by just having a simple average. There's a very popular algorithm that weights the replies based on the number of data points that each of the parties has. That's another, but there's a whole set, and maybe I can just show you just to give you a sense of how big it is here. So this is actually something that's this whole set of algorithms here that these are the basic ones, but there's also a bunch of them that are advanced algorithms that try, for instance, to exploit the structure of the neural network. Some of them, as you can see here, are for XGBoost, which is another algorithm that you can train. We have things special for differential privacy and to protect privacy and so forth. So there's robustness algorithms, all sorts of things.
I see. So there's many options for the way that this this combined model is created.
Indeed, yes. That's one of the interesting things about federated learning, and it's kind of a very productive research area in that there are a lot of issues. Each of the parties or banks or smartphones may have data that it's not necessarily distributed according to the same distribution. So these algorithms tend to work to overcome those barriers.
Got it. And I wanted to ask you specifically about the federated averaging algorithm. Is that one of the original algorithms used for this type of work?
Yes, FedAv was one of the main ones because it's very simple. So you take the replies and weight them by the number of samples. So if the two of us are training a machine learning model and I have 100 points, my replies, and you only have 5, my replies will have higher weight because I'm contributing more to the
Got it.
system. Yeah.
Got
Yeah.
it.
Yeah.
Well, that's fascinating, Nathalie. Thanks for explaining how that works. And it sounds like, as you mentioned, federated learning can be applied to more traditional machine learning models, to neural networks, to it's being used. It's sort of a mathematical solution that's being used across the field. It sounds like. Is that right?
Yes, yes. And the algorithm that you run, it's really dependent on what
Mm,
machine learning model you're running, you're trying to
mm-hmm,
get at the end
mm-hmm.
of the day.
Got it. Cool. Well, let's talk a little bit. Let's move from that into the combination, essentially, of the two topics, which is federated learning plus new attacks, because your career has been about sort of blending the security of something with data about something, and so it seems like there's a clear path now for you to start to research not just federated learning, but also some of the attack surface on federated learning. Is that fair?
That is exactly what I'm
Mm-hmm.
doing right now, and what my research is currently about is really trying to get federated learning, see what can go wrong, and then trying to solve it. I can again share like some slides. I think that maybe
Okay, that'd be great.
easier to kind of explain. But basically, there are kind of I just uh, let me just look for it. But basically, there are kind of different threat models for federated learning, and the one of the key things, if anyone in the audience is in the security field, the first very thing that you do is try to see what can go wrong and see what's the
Mm-hmm.
risk. And
Mm-hmm.
so one of the risks that we have, it's actually related to inference attacks. So remember here, over here, I will reanimate this one.
Mm-hmm.
Uh, we didn't exchange this data, but usually if you don't exchange, does it mean that you're really private, and does it mean that that's enough? And if you're a security person, you will tell me, depends. I cannot answer that question just
Mm-hmm.
yet. Give me the context. So it turns out if the company is the same, that it has all these parties and they just have the data in different clouds, that's enough. That's most probably enough. Just not to transmit the data, maybe just enough. But if you are in a more untrusted environment, there are two things that may go wrong. The first one is inference threats. So, and here it's what I mean. One of the issues that we have in the machine learning world is that once you publish a model, then an adversary may try to know whether a training point was part of that model. So this is the training data, and the adversary basically is trying to query whether Bob was part of the training data.
Mm-hmm. Mm-hmm.
And you may think to yourself, why would the adversary want to do that? Now, imagine that you know that this training set was collected for people that had AIDS. Then all of the sudden, you already know that
Mm-hmm.
Bob happens to have AIDS, which is a privacy violation.
Mm-hmm.
Uh, in a more enterprise setting, it may be that the adversary is trying to see whether somebody is going to acquire a startup, and that may be part of the training data that was used, all the documents and so forth.
Mm-hmm.
Then that's problematic again. So that's one of the threats. This is not specific to federated learning, but it's really all across. Every time you have a single model that you have trained and you put in the wild and people can query, then we have this problem. This other threat is really specific to the federated learning, in that here we are talking about these replies that are sent throughout the training process. And in this case, there are a bunch of different attacks that people have proposed in the literature to know what data was used. So even though you're not really transmitting the data, it is possible to know, for instance, you transmitted a 0 as this example. If you're training model for text classification and you happen to use a bag of words, then it is easy to see that a position of non-zero means that somebody actually got a word. Again, in the example of I'm trying to buy a company that's really worrisome. And more recently, people have also tried to achieve the exfiltration of data. For instance, was somebody in the picture wearing glasses? Like some property that it's part of the sample, even if it's kind of something that was not even part of the original training decision that we're doing. So these are kind of the inference threats that may occur, and with legislations like GDPR and HIPAA, like people are getting worried about this.
So both of these threats are used to expose specific facets or aspects of the training data, or even down to individual level information that may have existed in the training data that was used to originally train the model.
Exactly. So we need to protect against this, and I could take you briefly through some of the solutions that we have, if that's interested.
Yeah, that would be great. I'm curious, like, have you seen like clear examples of this in the wild? Are there sort of known cases where models were attacked this way?
For this one, I think this one is a little bit more in the wild, as you say. I am not aware. I know there's this data set that where they keep all these different types of incidents that have occurred with machine learning models. I haven't checked if there's one for this particular use case. This one, I don't think there's somebody has actually said, hey, this is in the wild. It's probably very researchy right now.
Got it. Partly because it's sort of combined with the federated learning model, which probably isn't in widespread use yet, even though its adoption is increasing.
Exactly. Yeah.
Okay, great. Yeah, well, why don't you take us through some of the solutions? That'd be fascinating to better understand how to protect models against these kinds of attacks.
Yeah, so some of the solutions, the ones that are out there, for instance, is having some data noise added to each of the queries at the end before replying to the aggregator. And in that sense, you can think about it like a plausible deniability sort of thing, because you're adding this noise. So at the end of the day, what the aggregator gets and the reply that you're sending kind of has that issue. The problem, this is known as local differential privacy, and each of the parties has, because each of the parties adds their own noise. The problem with this is that this basically means that we have end time noise. That's a lot of noise. And when you have a lot of noise, what happens? Your model performance just drops and it's just plummets. So that's an issue. And we try to combine different techniques from the security field to reduce the amount of noise that we have. So solutions that use multivariate computation techniques, for instance, are important. Very briefly, multivariate computation techniques, that means is that if Pete sends me some ciphertext and that's encrypted to the aggregator, and I also send the aggregator my ciphertext encrypted, the aggregator can take both those ciphertexts and combine them and find a model update without ever decrypting the information. So if you combine that with differential privacy, you can actually kind of reduce the noise substantially. And that's kind of one of the things. And so I have this one that it's just like a match made in heaven. And just to see like you get like really good result. And I know I'm getting too technical, so I'm going to stop there just to say that part of the work that I do a lot is to try to reduce the training time and explore different crypto systems to see how we can target a bunch of different techniques. Yeah. So.
Yep, got it. And so a lot of your work sort of terminates in another open source project from IBM. Is that right? The Federated Learning Library. Does that include techniques for both using federated learning and also protected federated learning? Talk to us a little bit about what that toolkit is.
Okay, so IBM Federated Learning, we have a community edition and a product. The idea there is that we have compiled a set of different algorithms. And one thing that we notice is that if you try to do federated learning in reality, you do need like very strong plumbing because these parties are in one cloud. Some parties are in one cloud, some parties are in other data centers, some maybe behind firewalls. So remember, this is a completely different system. So we created something that allows us to easily deploy the code to each of the parties and each of the entities, and then communicate with an aggregator that can be either at the cloud, so as a service, or it can be in a private cloud, for instance, Cloud Pak for Data. So that it's kind of available in its the framework. IBM FL kind of has that. On top of that, we designed it so that when we come up with a new fusion algorithm or privacy mechanism, we can easily put it there and just basically start the entire federated learning process. The other interesting thing is that if you are a data scientist, and I kind of consider myself a little bit of a data scientist, I already know how to write my machine learning models in Keras. So I was really pushing for this requirement, and I want to use my Keras model, and I want to specify it the way I usually do. I want this to be magic for me. So you basically bring your model in Keras or in PyTorch or in sklearn, and at the end of the day, there's magic. And just through a YAML file, you get your final federated machine learning model.
Got it.
Yeah.
Very interesting. Well, we had an interesting comment here. Daniel is mentioning that model manipulation is actually confirmed in some music streaming scenarios, music recommendations, and top 10 lists, apparently. And it sounds like perhaps there was a data scientist or someone at Spotify who commented on this. So thanks, Daniel, for mentioning that. We'll make sure to check that out as an example of some of these attacks occurring in the wild. But that makes sense that it would occur in something like Spotify, where they're trying to rank music perhaps by popularity publicly.
You can see how somebody may want to do that. Yeah.
Right. Yeah, exactly. Well, the IBM Federated Learning Library sounds interesting. Nathalie, are there a lot of people contributing to this now? I'm sort of curious as to how this is being adopted across the industry, and if you're seeing some good traction in the project.
So we have the community edition that's available. It's for non-commercial use. And it's closed source. So at this stage, people cannot really, outside people from IBM cannot contribute. Yes, but we want a lot of research to be done in this area. That's why we are open this way for people to really do their research and non-commercial playing with it. Besides that, we have a product, and we have different scenarios where we have been trying to deploy it in different real systems. One of them is, for instance, for premature babies. This is a startup that's trying to create machine learning models to predict whether somebody is going to be needing a particular treatment. So that's something that it's out there. There's also in the imaging a scenario where different hospitals and different locations may have information like X-rays or MRIs and so forth. How can we use federated learning to get a better predictive model? That's another use case. Banks trying to see whether, for instance, there's fraud. For those of you that have tried to create a machine learning model that detects fraud, one thing that you would think right away is that there's a lot of data that is benign, but the percentage of data that you have to learn how to detect fraud is like super tiny. So every time that we want to detect fraud, federated learning helps, because that means that, for instance, companies, they all have more samples for fraud, and that way you kind of expand your knowledge in that unbalanced place of your data. Yeah.
Got it. And where can people find more work, more info on your work on the FL library?
I can share that.
Okay.
Let me share that slide so that I can actually give the different URLs. I'm not super used to WebEx, to Zoom, so about that, you probably notice that that's the case. Let's see. Where can I show this? Okay. Yeah, so I would love if you check it out and let me know what you think about our framework. We're always looking forward to learn what people have think about it. So this is this has internal webpage, but you can see here the external library for commercial use, and it's also available in IBM Watson Machine Learning. Yeah, so this is.
Oh, there we go.
Yes.
And this is how folks can contact you in case they want to weigh in or have further questions about federated learning. Indeed,
yes.
Excellent.
Also, if you like our framework, give us a star. I love stars.
Yeah, that's right. good old GitHub stars. Well, Nathalie, this has been a fun conversation, and I really appreciate you bringing your expertise to our community and talking about these interesting topics. I can see how it requires a lot of experience, from distributed systems to crypto to there's all kinds of interesting sort of complicated things converging in this field, and so it seems to be a very rewarding and challenging field. But I'm really grateful that you came to share your knowledge with us.
Thank you, Pete. My pleasure to be here. Love talking.
Yeah, awesome. Yeah. Okay, well, we'll talk to you soon.
Thank you.
Thanks to everyone for joining us. This has been a great episode, and as you know, we have other episodes coming up, which will be announced soon. Don't forget to sign off or sound off with your feedback. We love to hear what the community is thinking, and we hope you'll join us for another